So greetings everyone. So today we will going to talk about the DES algorithm, or also called Data Encryption Standard Algorithm. So we will learn about the history of DES, the definition of DES algorithm, understanding DES algorithm, the example or method of DES algorithm.
History of Data Encryption Standard. The Data Encryption Standard DES is a symmetric key encryption algorithm that was developed by IBM in the early 1970s and adopted by the United States government as an official standard for a secure and data communication in 1977. The development of DES began in the early 1970s when the US government was looking for a standard encryption algorithm that could be used to protect a sensitive government communication. IBM responded to the government request for proposal for submit a block zipper algorithm that used a 64-bit key and a series of mathematical transformation to encrypt and decrypt data.
After several rounds of testing and evaluation, IBM's algorithm was selected as the winner and was adopted by the National Bureau of Standards, now known as the National Institute of Standards and Technology, or NIST, as a federal standard for data encryption in year 1977. So, DES quickly became the most widely used encryption algorithm in the world, and it was used to protect a wide range of sensitive information, including financial transactions, military communications, and classified government documents. However, concerns about the security of DES began to emerge in the year 1990s as advances in computing power made it possible to break the encryption using brute force methods.
In response to this concern, NIST launched a competition in the late 90s to develop new encryption standard that would be more secure than DES. The competition led to develop of the Advanced Encryption Standard AES, which was adopted by NIST in 2001 and since become the most widely used encryption algorithm in the world. Despite its eventual replacement by AES, DES remained an important part of the history of cryptography and played a significant role in the development of modern encryption techniques.
So next, we are now going to the definition of Data Encryption Standard, or also called DES. The DES algorithm is a widely used encryption algorithm that has been used for decades to secure data communication. The algorithm is based on the principle of symmetric key cryptography, which means that the same key is used for both encryption and decryption. So in this report, we will discuss the steps involved in implementing the DES algorithm. So we are now going to the purpose of DES algorithm, or also called Data Encryption Standard, is to provide confidentiality and data integrity by encrypting electronic data. DES is a symmetric key encryption algorithm, which means that the same key is used for both encryption and decryption of the data. It is widely used in electronic communication systems to protect sensitive information such as financial transaction, email communication, and login credentials. The DES algorithm operates on 64-bit blocks of data and uses a 56-bit key for encryption and decryption. Although DES has been widely used in the past, its use has decreased due to vulnerability to brute force attacks, and it has been largely replaced by more secure encryption algorithms such as AES, or Advanced Encryption Standard. Understanding the DES algorithm. The DES algorithm uses a 64-bit key to encrypt and decrypt data. The key is divided into 16 to 48 B subkeys which are used in each round of the algorithm. The encryption and decryption process involves 16 rounds of permutation and substitution.
Steps in data encryption standard. Step 1. Key generation. The first step in implementing the DES algorithm is to generate the 16 subkeys. This is done by applying a series of permutation and substitutions to the 64-bit key. Step 2. Data encryption. The next step is to encrypt the data. The input data is divided into 64-bit blocks, which are then permuted and substituted using the 16 subkeys generated in previous step. Step 3. Data decryption. To decrypt the encrypted data, the same steps are followed but in reverse order. The encrypted data is divided into 64 bits block and permuted and substituted using the 16 subkeys in reverse order. Step 4. Validation. Once the data has been decrypted, it is important to validate the result to ensure that the decryption was successful. This can be done by comparing the decrypted data with the original data.
In data encryption standard, we have 64-bit blocks. For example, let's say we have a key value which is in our PowerPoint presentation now, and the first thing we need to do is to convert the key value into binary digits, which is the ones and zeros. Therefore, we generate our key value into 64 bits. Let's use the key that is presented on our PowerPoint. So, after when we compute it, this will be 64 and we label it into 4 for being able to know how to apply the table. The next thing we do now is to apply the permutation table. Now this PC1 that is presented also on our PowerPoint, to make it up 56 bits. Apply the PC1 table to the original 64-bit key to obtain a 56-bit key by selecting specific bits according to the positions in the PC1 table. The result is a 56-bit binary key. Add a parity bit to every 8 position to obtain a key of 64 bits. The parity bit ensures that each 8-bit block has an odd number of ones. And then, add an extra 0 bit to the beginning of the 64-bit key to make a total of 65 bits. So we have now the answer, which is presented on our presentation. After applying it, we need to divide it into 2 equal parts, which is also presented on our PowerPoint. And then, after dividing it into 2 equal parts, we now do the circular shifting or scheduling of iteration. Look up the number of positions to shift for the round in the shift table. Take the 28-bit half of the key C or D and split it into 2 parts, and then the n bits, where n is an shift amount, and then the remaining 28 n bits is circularly shift the second part, the 28 n bits, to the left by n positions, wrapping bit around from the left end to the right end. And then concatenated the first n bits with the shifted 28 n bits to obtain the new 28-bit half of the key. Repeat the process for the other 28-bit half of the key to obtain new values of C and then the number, and the D and also the number. It's either at 1 or 0. And then which are combined to generate the sub key for the round of encryption. Since we are getting the key 1, so the number of left shift is also 1. Therefore, one digit only needed to be moved into the left or in the last part. The answer is in our presentation. After that, we apply next the 48 bits, which is we will use the PC2 table. So the final result is in our PowerPoint presentation. After generating it, we will convert it to hexadecimal. So it will be now in our presentation. This would be now our key 1. We generate 16 subkeys from the original key using a key schedule algorithm. Each subkey is 48 bits long. For each of the 16 rounds of encryption, we perform the iteration to get all the subkeys. We also have here the plain text encryption. Just like earlier, we need to convert it first into the binary digits, and then we will now going to apply the initial permutation table. So the result is IP is equal to, and then it was presented in our presentation, and then convert it into the hexadecimal. We will going to split the result of the initial permutation into 2 equal parts again, so it will be like this. We will now get to the XOR by applying the E-bit table. So the R0 is equal to DC1 F1 0 F4 is the only thing we need to get this point. So convert it again into the binary digit and apply the E-bit table, and the result is in our presentation. And then convert it again in hexadecimal to get the XOR of it. And the key 1 we get earlier will be needed here and add it with the R0. After getting the XOR, we will now proceed into the S box. We split the 48-bit result into the 8 6-bit chunks. For each chunk, we look up a corresponding value from a predefined S box table and substitute it into the 6 bits. Next is permutation. We apply a fixed permutation to the result 32 bits. We XOR the permutated result with the left half of the data, which is the L0. We apply a final permutation to the data, which is the inverse of the initial permutation. And now finally, our output is here. The resulting 64-bit data is the encrypted ciphertext, and our encrypted message is in our presentation now.
Implementing the DES algorithm involves a series of complex steps that required a thorough understanding of symmetric keys cryptography. By following the step outlined in the report, you can successfully implement the DES algorithm and ensure your data communications. Important to note that while the DES algorithm has been widely used in the past, it has been replaced by more secure algorithms such as AES, which use longer keys length and stronger encryption methods.
So that's all our report. Thank you for watching and also listening.